Hey everybody, Dr. A here, and in this video we're going to be exploring another example of normal strain. So let's get started. Here we're being given a rigid beam that is supported by two wires and a pin. So here we see this rigid beam that is supported by a wire AD and a wire BE and then a pin at C. We're being asked to determine the normal strain in the two wires if point A displaces 1 inch downward. So point A is at the end here. It's attached to wire AD, and it displaces 1 inch downward. Okay. Now let's take a closer look at our figure. Wire AD is 2 feet long. Wire BE is 3 feet long. The distance from point A to point B on the beam is 2.5 feet. And the distance from point B to point C on the beam is 4 feet, okay? Now, the first thing I want to point out before we tackle the solution is we're being told that this is a rigid beam. In this context, what we mean by that is that we are not considering the beam itself deflecting or bending due to that applied force F, okay? So in reality, this beam would have some kind of deflection or bend due to the applied force F. And it would only be a little bit, but the amount that that beam would bend or deflect is considered to be very small compared to how much wire AD and BE will elongate. So by having this term rigid beam implanted into the problem statement, we are only going to be considering the elongation of wires AD and BE and not the actual deflection or bending of that beam, okay? So let's go ahead and get started. The first thing we're going to do is, because we know that point A displaces 1 inch downward, I'm going to go ahead and draw a diagram that shows the displacement of this system. So instead of drawing the thickness of the beam, I'm going to draw the beam as a straight line here. That's going to help me kind of simplify my, my diagram. And, you know, we've got this wire here, and we have this other wire here. All right. Now, I'm going to, in red, I'm going to show the displaced version of this beam. So we know point A displaces downward by 1 inch, okay? And so what I can do is show that this beam has rotated down, and let me draw this just a little bit better for us. There's that displacement of 1 inch, okay? And so what's happened is these wires AD and BE have elongated, okay? So this point down here, I'm going to call it A prime, and this point here, I'm going to call it B prime. That's where points A and B have displaced, okay? And again, we know that this is 2.5 feet, and we know that this is 4 feet. All right? So the first thing we can notice is, because we know that point A displaced downward 1 inch, I can say that, you know, delta A is that 1 inch. Now, ultimately, I need the strain in these two wires, okay? And we know that the basic definition of normal strain is a displacement over an original length, okay? So here's my question to you. Do I have enough information to get the strain in wire AD right now? The answer is yes, okay? So I can go ahead and get the strain in wire AD by just saying 1 inch divided by 24 inches. And I need 24 inches because I need consistent units. That's the 2 feet there, okay? So if I say 1 divided by 24, I get 0.0417 inches per inch, or you could just leave the units off of that completely. So if you recall, strain is dimensionless, but you can also leave the units there in terms of length per length, inches per inch, or you could just as easily express this as a percentage, and we could call this 4.17%, okay? So we got the strain in wire AD, that's easy enough. What about the strain in BE, okay? Well, what we need in order to get the strain in BE is the displacement of point B. So what we need is delta B here, okay? Now, do we know delta B immediately? Well, no, but we have information that will allow us to figure out what delta B is. And that information has to do with relating these similar triangles to one another. So if you notice, we have one big right triangle here, okay? Here's one big right triangle, all right? Now we have a smaller right triangle that's formed with point B, okay? Now these two right triangles are similar triangles. We know that they're similar triangles because they share a common interior angle right here, all right? Now what we can do is set up a proportionality with these two right triangles. So here's what I can do. I can say delta A divided by the total length of that bigger triangle, which is 6.5 feet, equals delta B divided by the length of the smaller triangle. So what I'm doing is I'm looking at a ratio of this vertical dimension to the horizontal dimension of the larger right triangle, and I'm setting that equal or proportional to the ratio of the vertical dimension to the horizontal dimension of the smaller right triangle, okay? And so what I can do then is say, well, delta B is going to be equal to 4 feet over 6.5 feet times delta A. So that's going to be 4 feet over 6.5 feet times the 1 inch. And so what does that come out to be? Well, we say 4 divided by 6.5 times 1 inch, and we get 0.6154 inches, okay? So that 0.6154 inches is the vertical displacement of point B in our system. Now, you might be wondering, why did I not convert the 6.5 feet and the 4 feet? Why did I not convert those to inches? Well, I could have if I wanted to, but if you notice when we set up these similar triangles, the feet units will immediately cancel, okay? So we're basically just scaling down delta A by this ratio of 4 feet to 6.5 feet. So could I have multiplied this numerator by 12 and this denominator by 12 to convert 4 and 6.5 to inches? Sure, I could have, but you're really just multiplying the numerator and the denominator by 12, which is still canceling itself out. So you will still end up with 0.6154 inches as delta B. Now, again, earlier when we calculated the strain in AD, we weren't scaling anything. We were literally saying 1 inch over the original length of member AD. And so that one we had to convert to 24 inches because we had to maintain those consistent units with strain. But here we're just scaling a dimension, okay? We're scaling a displacement based on 4 feet over 6.5 feet. Again, converting to inches, we'll just insert a 12 in the numerator and the denominator, which would cancel itself out anyway. Okay, so that's my my 2 cents on similar triangles. Now let's go ahead and calculate that strain in, what do we need? The strain in BE, okay? So the strain in BE is going to be equal to 0.6154 inches divided by the original length, which was 3 feet in wire BE, which is 36 inches. And so let's punch that through in our calculator, 6154 divided by 36. And so here I get 0.0171 inches per inch, or you could say that this is 1.71 So here are two answers. There's normal strain BE and normal strain AD. Again, you can keep this in terms of inches per inch, or you could just not write inches per inch and just, say the number itself because inches over inches cancel, or you could express it as a percentage. Either of those is acceptable. You just need to look carefully at a problem statement for a quiz, exam, or homework assignment that you might have, just to make sure you're answering the question in the way the problem is asking. Okay, so if you found this video helpful, please hit like and subscribe and be on the lookout for other similar content. Thanks for watching.